One last idea about trees is that they can represent more complicated kinds of data by using multiple mutually recursive types. For example, let's say I'm building a flowchart to plan out the actions of my day. I have here the flowchart. I start off at home, and I have the choices of either sleeping or driving. If I go back to sleep, it's a successful day, but if I decide to drive to school, then I'm met with new options. Either I have to sleep, in which case I get in trouble and get fired, or I teach, and everyone gets more successful. So let me represent this using not just a binary tree, but a more complicated representation. We'll start by saying an outcome is either a string, unequivocally, and it's either success or failure. So that represents these end nodes, the success and failures. Then we'll need a plan is either an outcome or a step, which we haven't talked about yet. So this is representing the whole deal, the whole shebang. The plan is either the outcome or the step. We'll define struct to get a step. It is a name and has option 1, option 2 as part of it. So a step is a make step, string action. And the steps represent the home, school aspects of this flowchart. They are the individual possible phases. We say that a plan is either one of these steps or it's success, so it's one of the outcomes. So each of these different things represents a plan. But we also need to represent the things connecting the steps together. We'll call those actions. So we need one more struct. Define struct action, has a name and a next, and an action is a make action, string, and a plan. So we need these names here to represent the text on the flowchart, but the next is going to represent the next action available. So if I sleep, the next step, the next outcome, the next plan is success. And that's why the type of it is plan, because an action can lead either an outcome or a step. So it has to be a plan. All right. So let's make an example of the diagram above. We'll copy and paste it onto the interactions window so that I can keep track of it. And we'll say that today's plan are to make a step. That's home is the starting point. And that has two potential options. I can, and let's do a ... for each one. For the first option, I can take the action of sleeping, in which case it leads to success. So that's this entire path. The other option that I've got is to drive in to work, or rather to school, in which case if I do that, then I've got a new step available at school, and that has two options itself. So the first option is the possibility of taking the action of sleeping, in which case I get to failure. And the other option is to teach, in which case I reach success. So this models the whole diagram shown there by combining steps, actions, and outcomes to make a big plan. Writing functions over these data structures is a little more complicated. As an example, let's count the number of ways that my day can end in success. So if we count success, we'll have a plan, and it produces a number. Consumes a plan and produces the number of times that plan ends in success. Okay, so we need to define count success as a function that consumes a plan, does something. And we'll write check expects. If we count success on the simplest kind of plan, the simplest kind of, which is an outcome, which is a type of plan, then we have one potential success. If the outcome of failure was used, we get 0. And if we count the number of successes in a more complicated structure, like today's plans, then we end up with 2 potential successes by either sleeping or driving to school and teaching. Either one is a good day. Now we need to go write our actual function. It would use the template for a plan. In this case, a plan is a itemization, so it's a conditional, and it's either a string, in which case it's an outcome, because an outcome is a string, and we'll do something. Otherwise, it must be a step, in which case we need to do something else using the two steps options. So we would put in here doing something with the, potentially, with the step name of the plan and the recursive call, not a recursive call, I'll come to this in a second, step option 1 of the plan. So this is just based off the selectors. Actually, let's slow down and just go based off the selectors for now. We have something to do with the two options. Now, when we're counting success of a plan, the outcome situation, which is sort of like our base case, is pretty straightforward. If the string is equal to success, if the plan is currently success, then we got a success, and that's great. We return 1, otherwise we return 0. So in this case, a plan was an outcome. An outcome is either success or failure. If it was success, we return 1, otherwise we return 0. Okay, that's one case. In the case of a step, we don't need to know anything about the name of the step. That isn't relevant. But we do need to know what about the number of successes following the first option and the number of successes following the second option. And we need to know the total of those, so we'll end up combining them together. But step option 1 is a selector on plans that produces an action. And we can't add together actions. We want to count the number of successes for those actions. I'm going to write a function right now. I'm going to write a function call for a function that doesn't exist. Now, I have this count success action. If I had it, it'd be a function that consumes an action and produces the number of successes for it. So I've suggested this function should exist. Let's manifest it. Let's make it actually happen. So this is count success rate. Consumes an action, produces a number, consumes an action, and produces the number of times that the next steps of that action can end in success. This will be this header, count success action, consumes an action, does something. Write a couple of check expects. This is a pretty straightforward case. We can count success action, give it a action, like if I sleep, which leads to the outcome of success, then I get 1. Or if I lose, which leads to the outcome of failure, then I get 0. So this is all based on my action, which has a name and a next. That next being a plan itself. I made both of my check expects plans just be simple outcomes. Could have embedded a whole other step instead. And we just need to figure out how to count the success of an action. We know that this is a function that consumes an action, so we know that we'll need at least one of the selectors of the action. Since we don't need to care about the name of the action, we just need its next. And we have the next of an action, which is a plan, and we just need to count the number of successes for a plan. And it turns out we have a function that does just that. Count success is a function that consumes a plan, produces the number of successes. And action next produces a plan. So we just need to combine all these together. Count success of the action next. Run it and find out if it works. And it does. So we made a very complex data representation here to model a more interesting situation than just a binary tree. And we end up needing a couple different structs and an itemization and enumeration. And we needed functions that, rather than calling themselves, called other functions that in turn called the original recursive function. This is a much more complicated data representation, but allows us to represent more complicated phenomena, usually the trade-off of things.